The laws introduced in the last section are all empirical laws. They describe the macroscopic properties of gases observed in experiments. However, gases are composed of atoms or molecules. To understand the properties of gases, we have to discuss the microscopic behaviors of gas particles. We will see that temperature reflexes the energies of particles. Pressure is caused by the impulse of the collisions of particles with the wall of its container. We will discuss the kinetics of particles in ideal gases. An ideal gas is defined based on a few assumptions of the behaviors of its particles. First, the number of particles in the gas is very large. Thus, the macroscopic properties of the gas are the results of the collective behaviors of all the particles. Second, each particle is a point in the space. The volume of the particles is neglected. Third, there is no interaction between particles. It is true when the particles are far enough from each other. Fourth, since there is no interaction between particles, they move with constant velocities between collisions with walls. The particles change their velocity only when they collide with the walls. Fifth, the collision time is negligible. The particles change their velocity immediately after the collisions. Sixth, after the collision, the velocity component perpendicular to the wall is reversed. It is like the bounce of elastic balls without energy loss. Now, let's consider the pressure of ideal gas caused by the collisions of particles with the wall of the container. Suppose the container is a cube with length of L. A particle moves in a velocity v. The x component of velocity is vx. When it collides with the wall perpendicular to the x-axis, the x component of velocity becomes minus vx. So, the impulse to the wall, that is, the opposite of the momentum change, is 2mvx. M is the mass of the particle. According to Newton's second law of motion, force is equal to the rate of the change of momentum. In the integral form, the impulse is the integral of force with respect to time. It is also equal to the product of mean force and duration. Between two collisions with the same wall perpendicular to the x-axis, the particle travels back and forth in the container. The distance it travels in x direction is 2L. Thus, the duration between two collisions is 2L divided by Vx. Now, we have the mean force from one particle. It is proportional to Vx square. The total force is the sum of the forces from all the particles. It is equal to the number of particles times the mean of the Vx square. Pressure is force per unit area. Here, L cubic is the volume of the container. As a vector in three-dimensional space, the square of velocity is the sum of the squares of the speeds in three directions respectively. Since gas is isotropic, the means of the squares of the speeds in three directions are identical. So, mean of v square is 3 times of mean of Vx square. Finally, we have the pressure in terms of number, mass and mean of v square of the particles, and the volume. Pay attention that half mv square is the kinetic energy of the translation of the particle. Combining this result with the ideal gas law, we found that temperature is proportional to the mean translational energy of particles. The particles can also have rotational and vibrational energies. The translational, rotational and vibrational energies are collectively referred to as thermal energy. Thus, temperature is the manifestation of thermal energy. It is the microscopic physical meaning of temperature. The root mean square speed is the square root of the mean square of velocity. It is one of the typical speeds of particles in gases. The root mean square speed is directly related to the speed of sound in the gas. For example, the root mean square speed of nitrogen at room temperature is about 515 meters per second. The speed of sound in the nitrogen is about 352 meters per second. Here, gamma is the adiabatic constant. For nitrogen at room temperature, gamma is 7/5. The speed distribution of particles in ideal gas is described by the Maxwell-Boltzmann distribution. It is derived with statistical mechanics, which is beyond the scope of general chemistry. Nevertheless, we can still discuss the characters of Maxwell-Boltzmann distribution. The distribution function depends on the ratio between the mass of the particles and temperature. At fixed temperature, the distribution function becomes higher and narrower with the mass of particles. At fixed mass of particles, the distribution function becomes lower and wider with temperature. The mean kinetic energy can be calculated from the Maxwell-Boltzmann distribution. You can check the calculation process by yourself. The resultant mean kinetic energy is the same as calculated from the kinetic theory of gases. The mean speed can also be calculated. Pay attention, it is not equal to the root mean square speed.